Hello everyone, I am Peti Sharath and today I am going to present my project. This project was titled as 3D Object Mission and Classification using Artificial Intelligence. This project was developed as part of my AIML coursework and it explores how artificial intelligence can analyze and classify 3D objects through their geometric features without relying on textures or images. In this presentation, I will take you through the motivation, methodology, code implementation, results, and how this project opens up new possibilities in 3D object understanding. Next, the problem. In today's 3D modeling and industrial design workflows, objects are represented as meshes. Meshes are collection of thousands of small triangles forming the surface of a model. Traditionally, classifying or identifying these objects is done manually through visual inspection or file name conventions. But this is inefficient, subjective, and prone to error, especially when we work with large data sheets or subtle shape differences. Then we can't be able to configure different models. The core problem was here that can we teach an AI system to automatically classify 3D meshes based on their structure? For that, my solution integrates Open3D, Python, and machine learning to extract mathematical features from 3D meshes such as number of vertices, faces, surface area, and bounding box volume, and then train a classifier that learns to recognize and visualize these object categories automatically. Next, the aim and objectives of this project. The aim of this project is to create an intelligent system that can classify 3D mesh models automatically by analyzing their geometric structure. These objectives were fourfold: to construct and refine 3D meshes using Blender and MeshLab, to extract key geometric features, vertices such as vertices, faces, surface area, and volume using the Open3D library. Then, to train a random forest classifier that learns patterns across different object categories. And finally, to evaluate model accuracy and visualize 3D structures interactively, which we will be going through further of the presentation. Together, these objectives form a full end-to-end pipeline from 3D models to an intelligent, interpretable AI classification system. So, to build this project, I require few tools and datasets. So, the tools and datasets were for this project, I used a combination of 3D design and AI tools. Blender and MeshLab were used for mesh modeling, cleanup, and exporting .off files. Open3D handled mesh processing, geometry analysis, and visualization. Pandas, NumPy, and scikit-learn supported data handling and model training. The dataset was ModelNet 40, one of the well-known 3D CAD datasets consisting of 35 categories and over 12,000 3D models including chairs, cars, tables, lamps, and many other day-to-day life 3D objects. The combination of these tools ensured both geometric precision and analytical accuracy, bridging the gap between CAD design and AI-based interpretation. Now, the methodology and demonstration overview. Here is the complete workflow. First, 3D mesh data was collected from ModelNet 40. In the phase 1, we extracted structural features like the number of vertices, number of faces, surface area, and bounding box volume using Open3D. In phase 2, we extracted features. The extracted features were stored in CSV file and used as an input for a random forest classifier, which led to recognize objects based on these numeric descriptors. Finally, in phase 3, a visualization model allowed interactive 3D exploration where users can view meshes category wise and analyze their geometric differences visually. The methodology thus combines geometric processing, AI classification, and visualization, forming a complete analytical pipeline. Now, coming to the initial workflow, feature extraction. First, I will demonstrate the code, then first I will show the code, then I will demonstrate the code for you. The script The feature extraction phase was implemented through the first Python script, extract features.py. The script begins by importing essential libraries such as Open3D for mesh reading, NumPy for numerical computation, and Pandas for data storage. The key function extract mesh features opens each .off file, fixes malformed headers, and loads the mesh into memory using Open3D's geometric utilities. It, compu- it computes four major attributes. First one is number of vertices, second one is number of faces, then comes surface area, and finally volume of the bounding box. Then the second function, extract all features, iterates over all 35 object categories and compiles these metrics into a structured pandas data frame. Then the final output is stored in mesh features, which serves as a foundation for the machine learning phase. You can see in the output that every row represents one object labeled by category and described by its geometric properties. This effectively converts complex 3D shapes into structured data that an algorithm can interpret. Now we will see the demonstration of how this thing works. As we have seen the demonstration of feature extraction, now we'll continue to object classification. The classification stage was implemented using the classifyObjects.py script. Here, I loaded the CSV generated earlier, isolated the geometric features such as vertices, faces, surface area, and volume, and encoded the categorical labels using label encoder. The data was then split into training and testing sets with an 80 is to 20 ratio, where 80% of the data was for the training and 20% of the data was to setting and testing, and standardized using standard scaler for numerical stability. For the model, I used a random forest classifier chosen for its robustness and interpretability. After tuning hyperparameters such as n estimators and max depth, the model achieved around 62% accuracy, a significant improvement over the initial 38%. The classification report displayed precision and recall values across all 35 categories, confirming that distinct shapes like cars, bathtubs, and toilets were easily recognized, whereas structurally similar items like tables and desks shows moderate confusion. I also visualized the confusion matrix and feature importance chart, which revealed the surface area and volume were the most discriminative features in object identification. Now now we'll see the demonstration and the confusion matrix of the object classification. We'll see the accuracy chart and all. Okay, as we have seen the confusion matrix, now we move on to the visualization phase. The visualization stage was implemented in visualize mesh.py, a fully interactive 3D viewer powered by Open3D. When executed the program, list all 35 categories, allowing users to type a category name such as chair or radio. Once selected, the program randomly picks and displays one 3D mesh from that category. Users can rotate, zoom, and inspect the model in real time. After viewing, the user can press enter to see another mesh from the same category, C to switch to a different one, or Q to quit. This continuous interaction not only demonstrates how geometric feature translates visually, but also provides tangible insight into why the classifier ground grouped certain objects together. In the demonstration video, I showcased the tool by exploring a few categories such as chairs, radios, tables, cars, showing how geometric patterns vary across them. We'll continue after the video. After completing all three stages, extraction, classification, and visualization, analyze the performance and interpretability of the system. The model achieved a classification accuracy of 62% with macro and weighted F1 scores at around 0.61. From the results, categories with distant geometries like bathtubs and curves were recognized accurately. Confusion appeared between similar shapes like table and desk or chair and stool. Balance scaling of features improved model stability, reducing overfitting. The visualization provided interpretability. We could now see why certain classes overlap by examining their geometric resemblance. These insights demonstrate that geometry alone can include a substantial amount of shape information even without textures or images. Then, the last, the challenges and the future scope of this project, the conclusive part. Like every research project, this one had its challenges. The ModelNet 40 dataset is large, and many meshes are noisy or incomplete, leading to inconsistent feature extraction. Class imbalance across categories caused unequal training performance. Since only geometric attributes were used, the model lacked schematic depth. It could differentiate between objects that are geometrically similar but functionally different. For the future scope, I aim to integrate deep learning architectures like PointNet or graph neural networks, which can capture spatial hierarchies within 3D shapes. I also plan to combine geometric and visual features such as curvature, color, and texture to build a richer multimodal representation. Finally, I envision expanding this framework toward AR, VR applications and robotic perception, where real-time 3D objects recognize and play a transformative role. To conclude, this project demonstrated how artificial intelligence can interpret geometry, converting complex 3D meshes into meaningful, classifiable data. The combination of open 3D geometry for geometric processing and visualization for human interpretability make this pipeline both efficient and insightful. In short, this work serves as an early step towards geometry-driven intelligence, where AI not only sees 3D shapes but truly understands them. Thank you for the time.